so let's practice actually running a confidence interval with a word problem here. So we're going to run through doing the full steps. We're going to do the I construct fabulous confidence interval. So I, remember, stands for introduction, which is a restatement of what it is that we're going to be doing. Construct, that C is for conditions, which are going to be the same conditions we checked from last chapter. Fabulous is for formula, and so we're going to write out our formula and our plug-in and find the actual interval. And then confidence intervals is conclusion in context, and that's when we're going to do that statement that we talked about. So with this problem right here, suppose you took a simple random sample of beads from the container and got 107 red beads and 144 white beads. Calculate and interpret a 90% confidence interval for the proportion of red beads in the container. Your teacher claims 50% of the beads are red. Use your interval to comment on this claim. Okay, so what are we doing here? Well, we are going to calculate and interpret a 90% confidence interval for the proportion of red beads in this container. So we are going to calculate and interpret a 90% confidence interval for the proportion of red beads in this container. Okay. All right, so let's go ahead and then check our conditions. So first condition, simple random sample. Well, they took a simple random sample of beads, so sample is a simple random sample. Now, since we took a sample, then we need to make sure that the population is at least 10 times the sample size. Now, how big is a sample size? Well, if I got 107 red beads and 144 white beads in my sample, 107 plus 144, I picked 251 total beads out. Okay, so my sample size is 251 if I add those two together, right? 107, 144. Okay, the population would be all beads in the container. Now, I'm going to assume that there are lots and lots and lots and lots of beads and that this is okay so that we can assume independence. If this was a question on the AP exam, they would tell you, hey, there were 5,253 beads in this container. And then that way you would know what the population was and you would know that actually checked out. So, okay to assume independence. Okay, and then the last condition we need to check is we need to make sure that we can assume normality and check for normality when it's proportions. N times P needs to be greater than or equal to 10, and N times 1 minus P needs to be greater than or equal to 10. Okay, well, I don't know the true proportion. I have a claim, but I don't know the true proportion. When we're dealing with confidence intervals, all of my P's are going to wear hats because we're going to use what we calculated from our sample. So I need to know what P hat is. And you calculate P hat by taking the number that you're interested in divided by the sample size. Well, since I'm interested in red beads, there were 107 out of the 251 that were red. So 107 divided by 251 gives me a proportion of about 0.43. We'll round it to the nearest hundredth. So N is 251, so 43% of 251 is definitely greater than or equal to 10. And 251 times 1 minus 0.43, so that's 0.57. 57% of 251 is also okay. So okay to assume sampling distribution is normal like. Okay, nothing big so far, right? Introduction is just a restatement of the question to say that we need to tell what exactly we're about to do. Conditions are the same three conditions we've been using. Okay, so now we're ready to run the interval. And so we want to show the formula. Okay, now on your formula sheet, you have it in words. Your confidence interval starts with your statistic. Well, I'm talking about proportions here, right? So my statistic is P hat plus or minus your critical value, which is the number of standard deviations or away from the mean. And when we're talking about proportions, that's always in terms of Z, the number of standard deviations away from the mean. And then times the standard error of the statistic. If you flip your formula sheet over, all of your standard errors are right here. And remember, we talked about this before. Your standard errors are just your standard deviation with the parameters replaced by statistics. So it's still just the square root of p times 1 minus p over n. It's just that both my p's were hats because I don't know anything at all about the truth, about the true parameter. Okay, so statistic plus or minus critical value times standard error of the statistic. All right, so p hat we said was 0.43. Plus or minus. Z star. Okay, I got to find Z star. Remember, Z star depends on the confidence level. And my confidence level is 90%. So you're going to grab your Z chart. Okay, remember, if I'm looking at the middle 90%, that means there's 10% split in two, right? That means there's 5% in this tail and there's 5% in this tail. I can do one of two things. I can go to my Z chart and I can look in the center for the p-value closest to 0.05 and see what Z-score corresponds to that. Or we learned you can use your calculator. You can say second bars, go to inverse norm. Okay, sorry, I didn't show you second and then bars, and then go to inverse norm. And you type in the area there to the left, so that's 0.05. And then the mean is 0, standard deviation is 1, because Z-score at mean is 0, and the standard deviation for Z-scores are 1. And if you hit enter, there's your Z-score. Now remember, if it's to the lower end, it's going to be negative, and the upper boundary is going to be positive, but they're both 1.645. Okay. Now, if you looked this up on the chart, it's right between 1.64 and 1.65. If you picked either of those, or if you did 1.645, your numbers aren't going to be that far off. Okay. All right, then times the square root of 0.43 times 1 minus 0.43. I could have written that out. I will. And then divided by your sample size, 251. All right, what I want to do at this point is I want to crunch out the margin of error. Remember, the margin of error is everything after the plus or minus. So I have this point estimate of 0.43. But then I need to see what this is. So I'm going to take just a second. Let's see. We got 0.43 times 0.57. That's 1 minus 0.43. Divided by 251. Then the square root of that. So second square root, second answer. Excuse me. And then times 1.645. So my margin of error is 0.0514. I'm just going to leave it at 0.05. So that means that my interval is between, well, 0.43 minus 0.05, so that's 0.38, 0.43 plus 0.05, that's 0.48. And so all I have left to do now is to interpret. So we are blank percent confident, 90% confident that the interval from 0.38 to 0.48 captured, what was it we were trying to capture? Captured the true proportion of red beads in the container. Captured the true proportion of red beads in this container. And that's a confidence interval. Okay? So this is what needs to be shown as your work. It's a lot of work. It takes up a lot of room. But luckily, there aren't too many of these on the exam. The other good thing is they follow the same steps every single time. You start with your introduction, a restatement of what's going on. You check your conditions. Same conditions every time if it's proportions, sorry. Show your formula, show your plug-in, find the interval, and then your conclusion and context. Now, you can check yourself and find this interval using your calculator, and that's fine, okay? You need to show formula and plug in as part of your work, but if you would like to calculate this confidence interval on your calculator, you can do so. Let me show you how. So you're going to go to Stat, over to Calc, over to Test. All of our tests are at the top, all the intervals are towards the bottom. So we're going to go down here until you see a 1 proportion Z interval, okay? Let me go through that again. Stat, test, go down to 1 proportion Z interval. Okay? When you find that, hit enter. it's going to prompt you for a couple of things. It's going to ask you for X and N. Well, we have X and N, right? We just talked about that. X is how many of what I'm looking for. N is the total number in the sample, right? Now, be careful. Do not put decimals in for X or N. These are counts. If you put decimals in, it will give you an error. So X is 107 because there were 107 red beads. And N is 251 because there were 251 of them. C level is just your confidence level. So that's 90% or 0.9. And then if you hit calculate, notice that is exactly what we got. Actually, a little bit more accurate, right? Voila. All right, let's try another one. A recent poll found that 433 of the 1,548 randomly selected U.S. adults questioned felt that unemployment compensation should be extended an additional 6 months while the country is in its current economic downturn. We want to use this information to construct a 95% confidence interval to estimate the proportion of U.S. adults who feel this way. Okay, why don't you pause the video and see how much of this you can run through on your own, okay? Pause it and then come back and check, and I'll go over with you. Okay, let's see if you did okay. First thing you should have written is an introduction. So the introduction is what we're doing. We want to construct a 95% confidence interval to estimate the proportion of U.S. adults who feel unemployment compensation should be extended. Okay, so we are going to construct a 95% confidence interval to estimate the proportion of U.S. adults who feel unemployment compensation should be extended. Now, you'll see me, because I get lazy, abbreviate words and things like that, and I'm fine with you abbreviating words on assignments and exams and things in here. On the AP exam, try to write everything out as clear as possible because we don't want the reader or grader to have to guess at anything. Okay. All right, next we're ready for our conditions. So the first condition is it needs to be a simple random sample. And they told us they were randomly selected, so we're good. So sample is a simple random sample. Since they were selected randomly and without replacement, then I have to check the 10% condition. So I have to make sure the population is at least 10 times the sample size. So the population here will be all U.S. adults. And there's my sample size. There are definitely more than 15,480 adults, so that's good. So okay to assume independence. Okay. Then I got to check for normality. So n times p, and remember we don't know the true p, so we've got to use p hat. And n times 1 minus p, both need to be greater than or equal to 10. So n, the sample size here, is 1,548. P hat, okay, well we need to find p hat, right? So here is my statistic, 433 of these. So p hat, if I'm calculating p hat, remember that's x over n, right? So in this case, x is 433 out of the 1,548. So if we say 433 divided by 1,548, we get a p hat of 0.279, so we'll say 0.28. Okay. This is definitely good. And so this definitely should be as well. And so since those check out, so it's okay to assume, so okay. Okay to assume sampling distribution will be normal-like. Okay, so we've stated our introduction, we've checked our conditions, now we're ready for the actual plug-in. So let's show our formula, our statistic, plus or minus our critical value, times our standard error, which is just our standard deviation with p hats put in place of p. All right, so everywhere there's a p-hat, I'm putting a 0.28. Now, z-star. Okay, let's think about this for a second. On this one, I'm doing 95%, so that's the middle 95%, right? So that means I got 5% split in two for these two tails. So half of 5% is 2.5% or 0.025. So you can do one of two things. You can go to your table A and look up 0.025 in the center of the chart, and then go and find the z-scores that correspond to that. Or on your calculator, you can go to second bars, go down to inverse norm, put in the tail probability, 0.025. The mean for z-scores is 0, standard deviation is 1, and our z-score is negative 1.96 and positive 1.96. Now, since it already has the plus or minus there, I'm just putting 1.96 here as the z-star. And then times square root of 0.28 times 1 minus 0.28 divided by the sample size. Okay, again, I have my point estimate, and now I need to find the margin of error, so I need to crunch that out. So on my calculator, I'll say 0.28 times 0.72 divided by 1548, square root second answer, then times 1.96. And that gives me a margin of error of 0.02 if I round it. So plus or minus 2%. So between 0.26 and 0.30. And before I write my conclusion, if I want to check my answer and make sure I did it okay, remember how to run this interval on the calculator? Remember, go to stat, over to test, down to 1 proportion z interval. Now, remember, all the tests are at the beginning, so you got to go down to your intervals. So 1 proportion z interval. It's going to ask you for x and n. So x is what we have in the numerator over here, the total number I was looking for, so 433. N is the total number in your sample, so 1548. My confidence level is 0.95. And then we're going to hit calculate. And that's essentially what I got, right? We just rounded. And so we can finish this out with a conclusion. We are 95% confident that the interval from 0.26 to 0.30 captures, and then we want to make sure we state what we're trying to capture, the proportion of U.S. adults who feel unemployment compensation should be extended. Okay, now I just noticed I didn't finish the last question. So on this one, it just wanted us to find the actual parameter. But on the last one, I just happened to glance up there and realize I didn't answer the last question. The last question says, your teacher claims 50% of the beads are red. Based on the interval I found, is 50% a plausible value? No, 50% is not in this interval. So if I were commenting on this claim, I don't think the teacher knows what they're talking about, right? Since 50% is not contained in this interval, it's not a plausible value, I'm thinking 50% is not correct, okay? So anytime you're given these values, now I'm not guaranteed that the truth is there, but I'm 95% confident in this case, right, that I've captured the truth by using this method, okay? All right, one last thing here, and let's talk about choosing a sample size. So a lot of times when statisticians are starting studies, they decide how much margin of error they want, and then they go back, and what level of confidence, and then they go back and calculate what sample size they need, okay? And so in that case, they would plug in, okay, like let's say I want a margin of error of like 1%. So I plug in 0.01 for margin of error. And let's say I want a confidence level of 95%. Well, we just found z-star on the last one. Z-star would be 1.96. But what if I don't know any previous information on p-hats? Or maybe I have limited amount of information on p-hat from this particular situation. What can I do? So because the margin of error involves the sample proportion p-hat, a lot of times we have to guess. So sometimes you can use a guess for p-hat based on a past experience or a pilot study. But most of the time, you can just plug in 0.5 as the guess. And the reason why this works for p-hat is the margin of error is the largest when p-hat is 0.5. What that means is I'm erring on the side of caution. No matter what p-hat happens to be, I will have a margin of error of that much or less with a sample size I calculate here, okay? So if you're given a margin of error to calculate for and you're solving for n, but you weren't given a p-hat to use, plug in 0.5 as the guess and then solve it out and use that sample size, okay? And quite honestly, that way, this value would be at that margin of error or less, which is what we want to happen, okay? All right, let's try something with this and then we'll be done with our notes for today. All right, so a recent poll found that 433, and this is going back to the same question we just did, of the 1,548 randomly selected U.S. adults questioned, felt that unemployment compensation should be extended an additional 6 months while the country is in its current economic downturn. We want to use this information to construct a 95% confidence interval to estimate the proportion of U.S. adults who feel this way. Suppose you wanted to estimate the proportion of people who felt that unemployment compensation should be expanded with 95% confidence to within plus or minus 1.5%. Calculate how large a sample you would need. Okay, well, I'm going to use the formula we talked about on the last page. I know the margin of error is everything after the plus or minus. And after the plus or minus, we have our z star and we have our standard error. Okay, so I have my margin of error is 1.5%, so I can plug in for margin of error 0.015. That's 1.5%, right? Equals z star. Well, for 95%, if you look at our last question, we found that the z star there is 1.96. And then for p-hat, I can either use the p-hat from the sample that I have here, and if I use that's just one sample, right? And because of sampling variability, I might get different results. So what I'm going to do is I'm just going to err on the side of caution, and I'm going to use a p-hat of 0.5 because remember, that's going to give me a situation where I'm going to have that margin of error or less. So I'm just erring on the side of caution, okay? So now I just got a little algebra, right? I'm going to have to divide both sides by 1.96. So I'll go ahead and say 0.015 divided by 1.96, okay? Then I'm going to square it to get rid of the square root, so square both sides, okay? And then I need to multiply n over to the other side. So at that point, I have something like, I'm leaving everything on my calculator. Here, in fact, I'll show you what I did. So I divided that away, so it's divided over here. Then I squared it, so I have at this point 5.86 times 10 to the negative fifth, right? Equals, I need to multiply by n's. N is over here. 0.5 times 0.5 is 0.25. So what I've got to do at this point, again, by n by itself, is I've got to say 0.25 divided by all that. So on my calculator, I'm going to say 0.25 divided by, and see how it says entry right there? If you see, answer right there, I'm on the wrong button. If I do second answer, it pulls up the last answer, that whole gobbledygook there that I don't have to type. I love second answer button, right? Makes my life so much easier. Okay, so the n I get here is 4,268.4. Now I can't have a partial person, and I would rather err on the side of caution, so I'm going to say at least 4,269. Okay. If you wanted to have a margin of error of plus or minus 1.5% with 99% confidence, would your sample have to be larger, smaller, or the same size as the sample in part F? Okay, so what do we change here? We change the level of confidence. I increase the level of confidence, which then would expand the margin of error, wouldn't it? Okay, so if I'm increasing my confidence level, that's going to make my interval wider. Well, I want to keep the interval the same. So how can I offset making it wider? Well, I could increase my sample size. I would need a larger sample size in order to offset the width that comes with a higher level of confidence. Okay? This poll was conducted by randomly calling cell phone numbers. Explain how undercoverage could lead to a biased estimate in this case, and speculate about the direction of the bias. Well, if it's calling cell phone numbers, does everybody have a cell phone? Everybody have a cell phone? No, and some might be unlisted, or some might block calls that aren't in the context. So explain how undercoverage could lead to a biased estimate. Well, we could be undercovering either people who do not own a cell phone, or somehow have unknown numbers blocked. And so the direction of this bias, well, who might be more likely to not own a cell phone? Maybe unemployed people. And so if that's the case, then I might not be getting their opinion on this, and my actual estimate might be a little lower than what, or that the estimate I got from the sample might be a little lower than what actually did happen. Okay. All right. Go try some problems out with this. If you need a little extra help, let me know. Go back and look over how we went through the full problems on the last couple of pages, and make sure that you're comfortable with this process. All right, good luck.